Welcome back to our DECA 2 lecture on inference of security relevant methods for static code analysis. In this second video, we are going to present a recent research approach that we have published called SWAN, which is a classification of security relevant methods. In this video and in the following of this lecture, most of the content is based on two recent publications from our group. We have a full technical paper that was published at ISTA and also a tool paper published at ASE. You can check both of them if you're interested for more details either on the machine learning models or the experiments and the results that we have published, or even on the tool that we have also available as open source. So you can find the code and you can find some examples how to use it on our GitHub account. And then if you want, you can also have a look in our tool demo video, which will give you an overview of the main features of our SWAN Assist tool, which is an IntelliJ plugin. Further details on SWAN Assist we are going to talk in the next video. For now, we are mostly going to talk about SWAN and the core machine learning classifier. So SWAN is a detection of SRM for security weaknesses, and it is a typical supervised machine learning approach. And there is a classification of sources, sinks, and validators. In the group of validators, SWAN supports classification into sanitizers and authentication methods. Additionally, for each SRM, SWAN is able to classify the method into CWEs, or a specific security vulnerability type. Currently, SWAN has support for 7 different CWEs. As a supervised machine learning approach, we have classifier models, so we have a set of models. I'm going to explain more details how this is created and how these models are run in the pipeline. Then it is important that we define every method as a data point in our machine learning. So we are classifying methods, and for this we need two types of data. So we need a trained data and test data. Trained data are the methods for which we know the labels, and in SWAN we have created a trained data which was a manual selection of 235 methods. This is also available in our implementation, so you can have a look in those and how we modeled them. These are good examples that we use for the classifiers in SWAN. So then for all methods that we don't know the label, we consider them as trained data. So if you want to use SWAN, then any application code that you have or library code that you have, and you want to infer the methods from that set as SRMs, then all of those methods will be considered as test data. The trained data is actually used in combination with the features. So the features describe our data. Most of the features, all of the features actually in SWAN are binary features. So they describe only a single characteristic as true or false. So let's say we have a method, and a feature example would be if this method has a void return type. Okay, so this would describe this method, and this will be one feature, so is a void return type. And this is one of the features, and based on those features and based on the train data that we have collected manually, we have built a set of classifiers. So this is called the training of the classifiers. So, and then once we have the classifiers SWAN, we can run SWAN on any input, and this is our test data. So SWAN will get as input, technically speaking, it will be a jar file, for example, of your application, and we are using actually Suit to load these jar files and to calculate the features and to create the classifiers, and then to run the classifiers on the test data. When we run this, as an output, we get lists of security relevant methods. So this is a very high overview, and now we are going to see for each of these parts some of the important details. First, let's see what are the types of features that we have in SWAN. SWAN uses the source code information only. As I said, we are using Suit to load the test data. It is also used to train the classifier, so to load the training data and to calculate the features for the training data as well. So what we have actually in source is the method and the source code. So here is an example of get parameter, and we have a method signature, but also we have the body available, and the types of features that we have modeled in SWAN are in different groups. So we have types of feature that are based on the names of the methods. So for example, this one is actually this example, package name contains servlet, is a feature that checks whether the package name of the method contains the key servlet. Okay, so this will answer yes or no. So we are using this kind of heuristics because we would expect more likely that sources will be contained in servlet classes. Okay, so this is kind of the modeling we are using here. Another example is name-based for method names. So we have a feature type method name starts with, and then when we can create a specific feature instance, for example, for the keyword get. So we can have method name starts with get, and for this example, we will answer yes for get parameter. Other types are return types of specific method. In this case, we can check if the return type of is string. Also for many sources, this is very typical that we get a like string as a return value. So this is modeled, for example, in the classifier for strings for sources. Then we also have data flow based features. So there we actually may have an implemented small intra-procedural data flow analysis within the method, where we, for example, have a feature type that checks if there is a flow from a parameter to the return value. So this feature parameter to return will answer whether there is actually data flow between a parameter and return, and this is quite useful. We have learned in detecting actually sanitizers. Sanitizers will will get anything, any tainted information, and in the parameters they will do some kind of processing, and usually they will return this value. And also another type of features are like modifier based, where we check like if the method is public, if the method is static or private, and so on. So this is also another indicator for sources or things. They are most of the time declared as public. So this is the full set of features that we have in SWAN. As you see, there are only 25 types of features. So we have its implicit method, its anonymous class method, if a class contains name, and so on. And then you see for these we have the number of instances in the table is the number. So feature F1 is implicit method is only instantiated once. So in each classifier we have only one feature of this type. But when we have multiple, it makes more sense when the feature is generic with a generic type. Like here, feature 3 is class names contain, and then we have many different keywords that are defined, and each keyword here would be a separate instance of this feature. So in the entire SWAN pipeline, we have in total 206 feature instances, okay, and only 25 feature types. If you are more interested in details, like more examples of this, we have further in our paper. But let's see now how SWAN actually runs. So we have for each SRM and for each CVE individual classifier. So all these inner gray boxes are individual classifiers. And you see we have 2 rounds of classification. So as an input, we get the code base or any library code, a jar file that you want to classify. And SWAN will run two phases. In round 1, we will classify all the methods into different security relevant methods. And as I said, we support sources, sinks, sanitizers, and authentication methods. And all of these classifiers run actually individually, and they are all binary. This means every method from the code base will be classified as source or not source. So this will be done again with the classifier for sinks. We will get for every method information whether the method is source or not source, or a sink or not sink. And same for sanitizers. Exception is here for authentications. In the authentications we have multi-class classifier. We distinguish between authentication method that will authenticate users, like log in, sign in, and so on. Methods that will unauthenticate users, like log out, sign out, and so on. And then we also have a classification. We also have a class for neutral authentication methods, like is authenticated. So this was design decision we made to introduce a third class, because many of these methods we realized that are check only authentications, like is authenticated in many libraries. They are not performing any kind of authentication or unauthentication, and they were kind of causing our classifier to work incorrectly. So we decided to include those in a separate class label, so they get kind of filtered out. So the authentication classifier is like the only one exceptional that has 3 classes: authentications, for authenticating, not authenticating, and so-called neutral authentication. So they don't really does any authentication, but we want to filter them out. So once the first round is finished, what we will get is several lists of security relevant methods. So everything that was classified as sources will be put in one list as sinks and sanitizers, and then for authentication as well. And everything else that was not classified will be put in a different list, and we discard this information. In the second round, then, as you see, we get only the input is the security relevant methods that were labeled at least with 1 from those 4. And then we have support for these 7 CWEs. We do actually again classification. So we have, for each of these CWE, we have built an individual classifier, which is also a binary classifier, which will tell for each SRM that was as input given whether this SRM is relevant for this CWE. So what we get at the end is a vulnerability specific SRMs. So for each resulting list, we know for which vulnerability type this is relevant, and for each method in this list we know what type of SRM is. This is a fully automatic approach, and so we did some experiments which classifier to use. So if you have some background in machine learning, there are plenty of different classifiers. Our implementation is based on DECA. This is an open source library written in Java and can be quite easily used. There is a command line tool, as well as there is a graphical user interface, but we used, of course, the command line tool to implement SWAN. So we call the classifiers, and there are different classifiers implemented. These are the results that we just calculated precision and recall on our training data. So I mentioned earlier we have training data that we manually selected. These are around 235 methods for which we know the labels. And in DECA you can perform quite easily cross-validation. This means the training data will be split within in 10 subsets, and then for each of the subset we are declaring one to be training data and the other rest to be testing data, and then we create a classifier from this one subset and then test the rest of the methods, and then we compare for each of the methods if the classifier worked correct or incorrect. So we can calculate true positive, false positive, true negative, and false negatives, and based on this we are able to calculate precision and recall. So in this table you see for each classifier here what is the precision and recall on the training data after 10 cross-fault validations. So we used SVM, support vector machine classifier, bias network, naive bias, logarithmic regression, C4.5. This is a kind of decision tree classifier. Stump is also kind of tree classifier, and Reaper. So these are the classifiers that we tested, and as you see, based on these results, we get the best results for SVM. So we get the highest precisions, usually among all classifiers. On average, as you see, it's 90-90. Very close is bias network, but the default implementation now in SWAN is SVM. If you want to change the classifier, you can do this quite easily in the code, but if you don't do any changes, then so that you know you're going to run the SVM classifier. Okay, so just another tool to mention. This was an earlier work, and it was also published in our group. It's called SUSI. It was kind of a motivation for SWAN. This work is also working very similar from machine learning perspective. We also have classification of methods, and the focus here lies on Android APIs and only detection of sources and sinks. So this SUSI tool is also available as open source. You can have a look, and it was used for flow rate to generate and to infer sources sinks from the Android SDK. And as we saw in the beginning of this lecture, and float rate is only targeting data leaks, so all modeling and all types of features that were selected are targeted to data leaks problems. Okay, so instead of classification to different security vulnerabilities, SUSI is able to classify the sources and sinks in types like calendar, contact, database, and so on. It uses also predefined or manually selected training set with a feature set, and since this was motivation for SWAN, we actually reused the 10 types of feature types in SWAN, and there are 10 new that were added in SWAN. Since SWAN is a more general Java approach, it can work on any Java input. We needed to expand the feature types to make the classifiers more general. Also, I mentioned that SUSI is only Android specific, so it really focuses on the Android specific information in the JDK, and SWAN targets more broad way of Java application types. So then in our results, we have done some experiments to see how does SWAN actually compares to the existing approaches. So I said we compared it to SUSI. In the meanwhile, there was another extension of SUSI where they also tried to generalize SUSI for Java. So we used those two approaches, and we wanted to compare how all these three approaches will run on the Android JDK. So we run all these three on one same version of JDK, and then we randomly selected 50 sources and sinks. So the only thing we could compare here was sources and sinks, since SUSI and the extension of SUSI does not support validators. And then we manually classified them. Since, based on this, we are able to calculate precision, because we only have information whether the classified source and sink from each tool is true or false. So based on this, we calculated precision, and SWAN here showed the best results, but still, as you see, SUSI is still quite good, especially in sources classification. Then comparing these approaches, we also looked into the number of methods that each tool will create, and this Venn diagrams shows exactly this. On the left side we have number of sources, on the right side we have number of sinks. As you see, SWAN has the highest number of methods, and SAS is the extension of SUSY, so SAS, based on the author's name, has the smallest number of methods that will be classified. So it's mostly strict here, and it is interesting to see that actually all these machine learning approaches have a very small intersections. So from all the methods in the JDK, in the Android JDK, which are about 30,000, only around 420 sinks were identified by all three tools together, and only 241 sinks were in the intersection. One decision that we made for SWAN is that we wanted to make SWAN very general, because we do a further classification into security vulnerability types, and SWAN and SUSY and SAS are more focused on specific vulnerability, that is data leaks. So you could expect, of course, that the types of sources that are modeled and expected and sinks in SWAN will be much broader, because we want to target many different security vulnerabilities. And on its own, after the first phase, so this is after the first phase, using SWAN is not very useful. So you will come to a very high number of methods. I think around about third of the methods will be classified as at least source or sink, which means that very likely we have high number of false positives there. But SWAN is actually useful when we apply then the second phase. And for this, we wanted to see actually how precise is, and this is the next experiment that we performed. So we wanted to see how SWAN will perform on real-world Java libraries. And for this we took 12 popular Java libraries as test sets. You can read the names here, but we tried to cover different domains. So we have some examples from the mobile domain, then many web frameworks, because web development is quite important when we are talking about security vulnerabilities. Like we have here Spring, Spark, Struts, and JT, and so on. Then we also had one example from home automation. We took Eclipse, Smart Home, and then one utility framework from Apache. So all these 12 frameworks, we individually take them as testing sets for SWAN. And from each framework and from each class, by class we mean here source, sink, or any of the vulnerabilities classes, we selected randomly 50 methods, or less if there were less classified, and then we manually classified them. So that was taken as a ground truth in order to be able to calculate precision. In total, we had collected 3,885 methods. And based on these manual calculations that we did, SWAN yield a precision of 0.76 weighted mean. So this is how one would expect SWAN to run on real-world Java libraries. This was the overall all classifiers. And if we only see then the precision of after the first round, which is after classifying into SRM types, the precision is quite good, so we can get 82.6%. Whereas if we see the classification of the security types or the CWEs, we are quite lower, so we are 67.7%, which actually is the motivation to do something here more. So we wanted to improve this, and based on our experiments and our process of creating these classifiers, we learned that all these CWE classifiers need much more domain-specific information, which is also based on the actual test data. So the actual code base that we are using and the namings of these packages and classes are quite important. And if we have good examples of them into our training data, we were able to improve the classifiers quite. So this motivated us to work on semi-automatic approach, which is a SWAN assist, and we are going to talk about this in the following video.